4.4 is about L'Hopital's rule. We're going to apply L'Hopital's rule in situations where taking the limit gives us a 0 over 0 or infinity over infinity result. That's called an indeterminate form. First of all, we're talking about taking a limit of a quotient. And if the numerator goes to 0 as well as the denominator, or as the numerator goes to infinity while the denominator goes to infinity, you can apply L'Hopital's rule as long as the limit exists when you do that. L'Hopital's rule allows us to take the derivative of the numerator independent of the derivative of the denominator. So right here you could see I've taken the derivative of the numerator independent of taking the derivative of the denominator, and then I apply the limit. You can only do this when you have an indeterminate form of 0 over 0 or infinity over infinity. You can also apply it if the limit is one-sided or if the limit goes to infinity or negative infinity. If you happen to get it in this form, if it's not a fraction and instead you get infinity minus infinity or you get infinity times 0, that would be something you could switch into a quotient so that you could apply L'Hopital's rule. So we'll see that in our examples. First example, if we were to take the limit as x approaches 1 of the numerator, we would get 1 squared minus 1, which is 0. And the limit as x approaches 1 of natural log of x is natural log of 1, which is 0. What you might be tempted to do is write equals 0 over 0, but do not do that. You have to write the numerator separate from the denominator. If you write equals 0 over 0, you'll get it marked wrong. Now that we've established this would be 0 over 0 or an indeterminate form, we could say this is of the form, or you could write indeterminate form 0 over 0. You could write this is of the form 0 over 0, or you can write indeterminate form 0 over 0, which allows you to take the derivative of the top independent of the bottom. So I'm going to write LH for L'Hopital's to indicate to you that I'm taking the derivative. So the derivative of just the numerator is 2x minus 1. Now I'm going to take the derivative of the denominator, which is 1 over x. This was not quotient rule. Notice how I took the derivative of the top separate from taking the derivative of the bottom. Now if I try to take the limit, I get 2 times 1 minus 1 over 1 over 1, which is 1 over 1, which is 1. Next example. The limit as x approaches 0 of x minus sine x gives us 0 minus sine 0, which is 0 minus 0, which is 0. And the limit as x approaches 0 of x cubed is 0. This is of the form, or you could say indeterminate form, 0 over 0. You're going to apply L'Hopital's. So that will become the limit as x approaches 0 of 1 minus cosine x over 3x squared. If you go to take the limit this time, you're going to get the limit as x approaches 0 of 1 minus cosine x is actually 1 minus 1, or 0. And the limit as x approaches 0 of 3x squared is also going to give you 0. This is another indeterminate form, 0 over 0, so we're going to apply L'Hopital's again. So now we'll take the limit as x approaches 0 of sine x over 6x. That would give us an indeterminate form, 0 over 0. You can keep repeating this until you get a result. The derivative of sine is cosine, and the derivative of 6x is 6. So now the cosine of 0 over 6 is what I have, which is 1 over 6. So for each time, I want to explain that you've arrived at an indeterminate form. And now you know if you apply L'Hopital's and you get an indeterminate form again, you can repeat it. Here we have a difference. So in this limit, I'm getting 1 over sine 0 minus 1 over 0. This is an infinity minus infinity form. So this is indeterminate form, infinity minus infinity. What I'm going to do is get a common denominator. I'm going to turn this expression into a fraction. So rewrite the limit a common denominator would be multiplying the first fraction by x over x, so I get x in the numerator, and multiply the second fraction by sine over x sine x. Now when I apply the limit as x approaches 0 of x minus sine x, I'm getting 0 minus sine 0, which is 0, and the limit as x approaches 0 of x times sine x is 0 times sine of 0, which is 0. So this is indeterminate form, 0 over 0. I'm going to apply L'Hopital's. The new limit will be 1 minus cosine x over, and I have to do product rule here, so I'm going to set up product rule. I'll get x cosine x plus sine x. And if I evaluate the limit now, it would be of the form 0 over 0 again. The derivative of the numerator is sine x. The derivative of the denominator, I'm going to use product rule again. So I'll get negative x sine x plus cosine x, and then the derivative of sine is cosine. So this is the limit as x approaches 0 of sine x over negative x sine x plus 2 cosine x. In this case, we're going to get 0 in the numerator when we evaluate the limit, and then in the bottom we're going to get 0 plus 2 times 1. So we're actually getting 0 this time. The answer for the limit is 0. Fourth example, when I go to evaluate the limit, I'm getting 1 minus 0 over 0. So this is a 1 over 0 result. That means I cannot use L'Hopital's rule in this case. So what I'm going to have to do in this case is examine what's going on because it's a one-sided limit. So I'm going to look at the number line where x equals 0. And I know that I'm approaching it from the right. If I think about a number close to 0, like 0.1 is close to 0, when I look at the value of the expression 1 minus the square root 0.1 over 0.1, in the numerator, I have 1 minus a positive number. The square root of 0.1 is going to be a small number. I'm only subtracting a little bit away from 1, and it's going to be less than 1. So it'll still be positive in the numerator. And of course, 0.1 is positive in the denominator. So I have a positive over a positive. That means as we approach from the right side to 0, where the graph is actually headed to positive infinity. Because there's a vertical asymptote there, it's headed to positive infinity. So the solution for this limit, the limit as x approaches 0 from the right of 1 minus root x over x, is actually equal to positive infinity. So here's an example where you do not use L'Hopital's rule. I'm going to step back for a moment. I meant to point out that in the first example, our result was 1. So you see, if you walk up to this math problem and you write equals 0 over 0, equals an indeterminate form, and you leave that sitting there, and then later you find out that the limit actually equals 1, you see that it does not equal 0 over 0 literally, it equals 1 literally. To write equals 0 over 0 is incorrect, and you will be marked off for that. Be sure not to say your limit equals that indeterminate form. Our next example, if I evaluate the limit in this example, it is of the indeterminate form infinity over infinity. So I'm going to take the derivative of the numerator and then take the derivative of the denominator. The derivative of the numerator is e to the x. The derivative of the denominator is 1. So what we have when we evaluate the limit, we have a very large number on top and we have 1 on the bottom. So that means this is going to infinity. That is your answer for that example. Number 6, if you look at the numerator and take the limit, you end up getting sine of 0, which is 0. If you take the limit of the denominator, you end up getting 0. So this is the indeterminate form, 0 over 0. So if I use L'Hopital's rule on this, the new limit to find is cosine over 1, which is the cosine of 0, which is 1. So you should have already known that the limit as x approaches 0 of sine x over x is 1 from what we have done before. But now you can see where L'Hopital's rule would have helped us decide that earlier as well. Our next example involves tangent. We actually have two functions in there. We have x times tangent of 1 over x. So if you think about infinity here, we have a very large number going in for x, and then to put a large number in this fraction turns the fraction into 0. So this is like 0. And when you take the tangent of 0, you get 0. So this is the indeterminate form, infinity times 0. So what we're going to do is change that expression so it's in a fraction form. Rewrite limit as x approaches infinity. Leave tangent of 1 over x there, but take x and rewrite it. X is the same as x over 1. So x over 1 times the tangent. Well, if this is x over 1 times tangent, that's the same as tangent times x over 1, which is the same as tangent divided by 1 over x. So I'm going to rewrite this as tangent of 1 over x over 1 over x. Now when I evaluate with infinity, I end up getting a 0 over 0 indeterminate form. So remember, when I think of x as a very large number, each of these fractions is going to approach 0. So in the numerator, I'll still get tangent of 1 over x is 0. And then, of course, the fraction 1 over a very, very large number is 0. This is of the indeterminate form, 0 over 0. So apply L'Hopital's. So the limit as x approaches infinity. The derivative of tangent is secant squared. So write secant squared of 1 over x. Then you're going to have to multiply by the derivative of 1 over x. The derivative of 1 over x is negative 1 over x squared. So we had to do chain rule there. And then the derivative of 1 over x, of course, is negative 1 over x squared. And yes, you can cancel those two fractions. So we're actually taking the limit as x goes to infinity of secant squared of 1 over x. Now, of course, we're going to think of x as a very large number. So if x is a very large number, it's like we're taking the secant of 0. And secant is the reciprocal of cosine. So the cosine of 0 is 1. Therefore, the secant of 0 is 1. And then when you square it, you get 1. So the answer to this limit is 1. Next, we have a limit as x approaches 3. If I evaluate that, I get negative 6 in the numerator, and I get a 0 in the denominator. This is not an example where we can use L'Hopital's rule. So what I suggest you do is you look at the number line where x equals 3. You know that x equals 3 is creating a gap in the domain of this function. So there's a vertical asymptote happening at 3, and it's up to you to decide if the behavior of the graph is headed in the same direction on the right side and the left. This is not a one-sided limit, but the limits on both sides have to agree. So let's head in from the left and see what kind of value we would get. So a number just to the left of 3 would be something like 2.9. And if I substitute 2.9 into the expression, I would get a negative on the top, and 2.9 minus 3 is negative 0.1, but it gets squared. So anything down on the bottom is going to be positive because it's going to get squared. So that means it would be negative coming in from the left. Now we'll do the same thing on the right. If we pick a number just bigger than 3, like 3.1, when we substitute that in, the numerator is still going to be negative and the denominator is still going to be positive. So that is negative as well. Now the left hand and right hand limits do agree. They're both headed to negative infinity. So that means the limit equals negative infinity. Additional indeterminate form. So we have what's called a corollary, or a type of addition to L'Hopital's rule. So if you can get a limit on the natural log of the function, then the limit on the function is equal to e to that limit. So what we're going to do is we're going to take the log of the function, and when we get the limit, we'll go back and we'll exponentiate. So we'll take e to that power to undo the log. I'll show you. The first example, if we were to evaluate this x to the 1 over 1 minus x, we would be looking at x to the 1 over 0. And the 1 over 0 is going to take us to an infinity, because when you have 0 in the denominator, you're going to an infinity. You have a vertical asymptote. This is indeterminate form, 1 to the infinity. So what we're going to do is we're going to imagine the limit as x approaches 1 from the right. We're going to name that expression f, the function f. So the x to the 1 over 1 minus x is f. I'll write that down. F of x is going to be our x to the 1 over 1 minus x. Now I have a nice equation. What I'm going to do is take the natural log of both sides. After that step, I can now bring the exponent down on the right-hand side. So I have the natural log of f of x equals 1 over 1 minus x times the natural log of x. Go ahead and take the limit of both sides. So the limit as x approaches 1 from the right of the natural log of f of x on that side, and then on the right side, the limit as x approaches 1 from the right of this. I'm going to scooch the natural log on top of the fraction. We can do that. And let's evaluate. When I substitute 1 into the numerator, I get 0. So the limit as x approaches 1 from the right of natural log x is the natural log of 1, which is 0. And then the limit as x approaches 1 from the right of 1 minus x will get us 1 minus 1, or 0. So this is of the indeterminate form, 0 over 0. So I'm going to have to apply L'Hopital's rule here. So the limit, so the derivative of natural log x is 1 over x, and the derivative of 1 minus x is negative 1. Now when I try to take the limit, I'm going to get 1 over negative 1, which is negative 1. So that means the limit as x approaches 1 from the right of the natural log of f of x is negative 1. Now the limit of the natural log is the natural log of the limit. And if I exponentiate both sides, it looks like this. On the left, I have e to the natural log power, which just gives me the limit as x approaches 1 from the right of f of x. And on the right side, I have e to the negative 1 power. Well, you know, f of x was written up at the top. I came up with f of x. I said f of x was x to the 1 over 1 minus x. E to the negative 1 power is just 1 over e. So the answer to the problem is just 1 over e. We're going to do that again with the next example. If you go to evaluate the limit by substituting in 0, you're going to get 0 to the 0 power, because the limit as x goes to 0 of sine x is 0, and the limit as x goes to 0 of tangent is 0. 0 to the 0 power. This is an indeterminate form. I'm going to do the same thing as I did in the last problem. I'm going to declare that f of x, that expression, sine x to the tangent x power. Then I'll take the natural log of both sides. And I'm doing this every time because it'll help me get that tangent out of the exponent. So natural log of sine x to the tangent power. Now I can bring tangent out of the exponent spot. So I get tangent times the natural log of sine. This is going to be an indeterminate form still. So when I write out my limit as x approaches 0 from the right on this side, and then I write the limit. See, I'm going back to take the limit now that I've got the tangent out of the exponent spot. But if you just did straight substitution now, you're going to run into trouble again, because the tangent of 0 is 0. And the natural log of the sine of 0 is the natural log of 0. So we're talking about infinity there. It's coming in from the right. The natural log graph goes to infinity on the right, negative infinity specifically. So I have a 0 times infinity indeterminate form here. Indeterminate form, 0 times infinity, which you know now is a candidate for L'Hopital's rule. But in order to use L'Hopital's, you have to get it into fraction form. So I'm going to rewrite this limit on the right so it's in fraction form. Now I'm going to leave the natural log of sine x alone, and I'm going to flip tangent to the bottom of the denominator. So the reciprocal of tangent is cotangent. Now I have it in fraction form, And if I substitute 0 in now, I'm going to get infinity over infinity. So this one is infinity over infinity. I'm ready for L'Hopital's. So L'Hopital's says the derivative of the natural log is 1 over the argument, so that's 1 over sine. And then I have to do chain rule, so the derivative of sine is cosine. And then the derivative of cotangent is negative cosecant squared. Remember, with L'Hopital's, you take the derivative separately. This actually simplifies a little. We do have a sine in the bottom of the numerator, and we have 2 sines in the bottom of the denominator. So the 1 over sine in the numerator is going to cancel with one of these in the denominator. Now we have cosine in the numerator, and we have negative cosecant in the denominator. Can we try to evaluate for 0 now? Probably going to be a problem unless, before we evaluate for 0, let's change dividing by cosecant into multiplying by sine. Sine of 0 is 0, and the cosine of 0 is 1. So I'm getting this limit as 0. Now remember, this is the limit as x approaches 0 from the right of the natural log of f of x. And remember, when I have the limit of the natural log, I can take the natural log of the limit, and now I can exponentiate both sides. So this side is to a power of e, and the 0 is a power of e. E to the natural log just gives us that argument. So the limit as x approaches 0 of f of x equals e to the 0 power. And you know e to the 0 power is 1. So the limit as x approaches 0 from the right, f of x initially, all the way back up here, was sine to the power of tangent. So I'm going to write sine to the power of tangent is 1. That's our answer.